Hello everyone, I'm Prof.Joun. The second lecture is on numerical integration. I think numerical integration is very important for understanding some detail about the finite element interpolation. Let's consider the process of changing a definite integral ranging from a to b into standard form of integral ranging from -1 to 1 like this. In this case, this mapping function changes the original integral into standard form, for example. It should be noted that mapping function involves the interpolation function, implying that the interpolation functions are deeply related to transforming definite integral into standard form of integration. Of course, each element type has its own standard form with integration scheme. In this process, we utilize most important concepts of finite element analysis. Basically, integration along the line segment is summation of weighted length over the definitely defined region, as can be seen from definition of Riemann integral. Because the integration range is always mapped onto a fixed line segment from -1 to 1 in natural coordinate system, we will formulate numerical integration rule of standard form. Computer does not know the integration at all. Thus, we have to develop an algorithm of calculating any definite integral using given primitive functions, including multiplication and addition. In the numerical integration, a definite integral is approximately calculated by summing weighted values of integrand at the selected integration points, that is, multiplication of function values at the integration points and their associated weights. The minimization of numerical integration point is of great importance because a larger part of computation time is consumed in calculating the integral during finite analysis. The optimized scheme in terms of finite analysis is Gauss quadrature. With two-point Gauss quadrature formulated like this, we can calculate exact solution up to third order polynomial by calculating only two function values at cosine equals ±1 over square root of 3. Three-point Gauss quadrature is formulated by this relation, which gives us the exact solution when the integrand is up to fifth order polynomial. Even though there is a mathematical way to determine optimum integration points and their corresponding weights, we'd better simply understand the meaning of integration points and their corresponding weights by experiences. Let's calculate the integration points and their weights for two-point Gauss quadrature in a simple way, using a general third polynomial that is a plus b cosine plus c cosine squared plus d cosine cubed. By hand calculation, we obtain 2 times a plus 2 over 3 times c for the exact solution. We can make a formula to calculate approximately the integral using the two-point Gauss quadrature rule, as can be seen here. Comparing the exact solution with this approximation, we can assume by insight that W1 and W2 should be all unity, and the integration point should be ±1 over square root of 3, in order to make two-point Gauss quadrature rule give us exact solution. For example, we can verify that hand calculation of this integral equals exactly the approximation obtained by two-point Gauss quadrature. However, when we apply two-point Gauss quadrature to calculate this fifth order polynomial, the approximation isn't exact, and the error amounts to 4.8%. To contrarily, three-point Gauss quadrature gives us exact solution for this case, as can be seen here from this example. It is known that n-point Gauss-Quadrat rule predicts exact solution if the integrand is a polynomial of degree 2 times n minus 1 or less. This table exhibits all integration points and their associated weights for up to 10-point Gauss quadrature. This figure shows graphically the 1-point and 2-point Gauss quadrature, which is sufficient to give us some insight on Gauss quadrature. In many cases, 2-point Gauss quadrature is being employed for numerical integration. For some special case, when functions change so drastically, higher-order Gauss quadrature may or should be used. Up to now, we became to know how to calculate the element equation in a very systematic way. Left assembling them into finite equation in the matrix form, imposing boundary conditions and solving finite element equations. In this slide, we are going to study how to assemble each element equation into a matrix form finite equation. The dimensions of total stability matrix and force vector are calculated from number of nodes, sometimes with number of elements, and they should be initialized before assembling. This is the general form of element equation of the problem we are solving now. All elements of elementary stiffness matrix, denoted by small character Kij for element E, and all components of elemental force vector denoted by small letter Fi for E should be added to their corresponding elements of total stiffness matrix and components of total force vector respectively. When an element is defined by left node I and right node J, K11 for element E should be added to Kii in total stiffness matrix, K12 for element E to Kij, K21 for element E to Kji, etc. F1 for element E should be added to Fi, and F2 for element 2 should be added to Fj.